Welcome to section 4.4. We are going to do minimum, maximum, or maximum, minimum problems, whichever way you want to call it. And that's what section 4.4 is all about. Some students find these very challenging. Some students think these make it just a ton of sense. Finally, we're seeing a little bit of what derivatives can be used for. Please note that this video is going to contain a lot of examples. I may go a little quickly. That's why you can stop it and rewind and whatever. So these are the basic steps for solving maximum minimum problems. There are 5 steps. Draw a picture of the problem, label the parts, write an expression in terms of one variable, graph the function, solve the problem, interpret the solution. We may or may not do all those steps for every single problem, but that's what your book suggests. So anyway, let's start with the box problem. And by the way, we just did this in Algebra 2 as a little project, and you may not have done as many of these problems when you were in Algebra 2, but parts of this problem, and I told the kids when we did it, this is a calculus problem. But we just never use the derivatives on it in Algebra 2. Okay, you have a square sheet of cardboard. You're going to cut up squares of equal sides out of each corner and fold them up. Basically, you're going to make a box. And you want to find the dimension of the box with the maximum volume. All right, so the first thing you have to do is write a volume equation for this box. Volume equals length times width times height. So we are going to take the measurements of this box. Now, the height is X because you're going to fold up those boxes, okay, or fold up the sides. The one side here is this red line right here, which I've just made black. 18 inches is the entire length. So that side is 18 minus 2x. That's what this little bit is. And the same thing on the side too. So the length and the height are the same the same measurements. So volume equals 18 minus 2x's times 18 minus 2x's times an x. All right, so you multiply all those together using your FOILing methods and all of those great and wonderful things, and you should get 4x cubed minus 72 x's, x squareds actually, plus 324 x's. All right, what we want to do is take the derivative of this because we want to maximize the volume. So what we're going to do to maximize this equation is take the derivative, set it equal to 0, and that's how you get a maximum or a minimum. You might also get a minimum. So the derivative of this is 12x squared minus 144x is 24. That's the derivative. We set this equal to 0, and actually this does factor and that sort of thing. You could look this up on your calculator, which would be fine with me. But if you want to factor this, it turns out to be 12 times x minus 9. You factor out a 12 first, and then you can factor what's left. X minus 9 times x minus 3. All right, and so therefore, we set these 3 parts equal to 0. 12 can't equal 0. X minus 9 could equal 0. Therefore, x would equal 9. And x equals 3. All right, well, let's take a look. Now, we've got 2 answers of where we might have a maximum. Let's take a look at what happens if you plug a 9 into the 3 sides. Remember, we have length is 18 minus 2x. We have width is 18 minus 2x. And we have height is x. So these both work for x. What about if we plug a 3 into this? We get a good number. What about if we plug a 9 in there for our length? 9 means the length and the width is 0. Yeah, that's a real minimum box. Okay, so 9 is not make sense. All right, if you plug 9 into 18 minus 2x, you get a 0 length, 0 width. Makes no sense at all. Therefore, our x must be 3. Therefore, the height is 3. If we take 18 minus 6, we get the width is 12 and the length is 12. Those are the dimensions of the box with the maximum volume. Now, what we should actually do is check on either side of x equals 3 and check the sign of the derivative to make sure that it's a maximum. Therefore, the derivative over here between negative infinity and 3, actually it'd be between 0 and 3, and 3 and infinity would be between 3 and 9, actually. This would be 9, just because it's a real world problem. We can't have infinite sides. All right, so the sign of the derivative, which is this function right here, between 0 and 3 is equal to a positive number. And you can test me on this, increasing, and then it's decreasing on the right-hand side. That shows that, yes, this is a maximum. It does pass our test that it's increasing and decreasing. Oh yeah, the other test we could do would be take the second derivative. We could have used the second derivative test and plug in a 3. Okay, so second derivative of volume at 3, and that should equal a negative number, which means we have a maximum. Okay, and that's the second derivative test. Okay, all right, so we just proved that those are our maximums. Okay, next problem. Find two numbers whose sum is 20 and product is as large as possible. So we have x, and most of these problems are going to have two equations that most of the rest of these problems at least, have two equations, and you have to maximize some value, or minimize. And the product, x times y, is going to be large. All right, so x plus y equals 20. And the product x times y, let's just set that equal to some function. And that function, the product, we are going to maximize. So we're going to take the derivative of this. It's actually an xy, isn't it? We need to make it into an x. We're going to set that equal to 0. But we've got to mess around with this equation because we don't want to take, well, actually we could, but we don't want to take an implicit differentiation, especially when we have another equation. We can write y in terms of x's. If we subtract x from both sides, we get y is 20 minus x. So let's plug that in here and look at our new equation. X times 20 minus x, or 20x minus x squared. Okay, let's use that equation. Take the derivative of it, which is 20 minus 2x, and let's set that equal to 0. When we set that equal to 0, we get x equals negative 20 over negative 2, or 10. X equals 10. So if x equals 10, we take the x, plug it back into the equation up here, 20 minus 10. That means y is also equal to 10, and that gives us our maximum value. All right, now if we took the second derivative test, just to make sure, the second derivative at 10, the second derivative equals negative 2 everywhere. So this is definitely a maximum. So x times y, when they're both 10, gives us the product as large as possible. The next problem is more fun. A rectangle has its base on the x-axis and its upper two vertices on the parabola, 12 minus x squared. What is the largest area the rectangle can have, and what are its dimensions? All right, so this is one where using the steps of solving min-max problems, you want to draw a picture. All right, so largest area, always look for what are we trying to optimize. We're trying to optimize the area. So area is length times width. We need to do the length times width in terms of x's. All right, so rectangle has its base on the x-axis and its two upper vertices on the parabola. Okay, well luckily this parabola is symmetrical around the y-axis, right? So the 2 points here, even though we don't know what they are, we know their y value Their y value is 12 minus x squared, right? That's how high this rectangle is. We'll call that its width.
Good morning, Mrs.
So area equals, all right, so our width is 12 minus x squared. Now, I already drew this into the picture, but whenever, if you're using 12 minus x squared as your y, then your x value must be x. So here, your x value is actually negative x. Over here, your value is x. All right, if you add the width of these two, you get 2 x's. So the length, whatever you want to call it, the length is 2x. So our rectangle inside there is 2x times the y value, which is 12 minus x. Okay, that's probably the hardest part of this problem, right there. Okay, let's multiply these together, take the derivative, set it equal to 0. If you multiply these together, you get 24x minus 2x cubed. Take the derivative, set it equal to 0. The derivative is 24 minus 6x squared. If you calculate this, what are the x's? The x's are plus or minus 2. All right? Next, you have to go back and see, do those make any sense? Let's see. We want the dimensions of the rectangle. Well, the dimensions, you can't have a negative 2x, right? If you plug negative 2 in here, you don't get a normal value. So really, our answer is just positive 2. You can't have a negative side. So if the length is 2x, then our dimension is 2 times 2 when x is 2, so that's 4. Our width, 12 minus x squared. Plug in a 2, you get 12 minus 4 is 8. So the largest area is 4 times 8 equals 32. And that will be units squared, whatever the units are, because that's an area. This is A max. All right, that's your answer. These are your 2 dimensions. You're golden. Next problem. This is economics and maximizing profit. When you have revenue, R is revenue, C is cost. We did this once before. Profit is when you take revenue minus cost. If you take the derivative of the profit, set it equal to 0, that maximizes profit. Okay, and that's what we want to do. Well, that's what it says up here. I don't need to rewrite it. It says maximize profit. All right, so R minus C equals 0, the derivatives. Okay, so let's try a problem like that. If we want to maximize the profit for the revenue, we're going to take the profit equals the revenue minus the cost. This makes sense for anyone who's even thought about economics. I never liked economics. Ooh. But anyway, so the profit derivative, which we're going to set equal to 0 to maximize the profit, equals the derivative of the R, which is 10 minus 0.0002x. You have to be careful with these. And then you're going to subtract, and don't forget to subtract both things. 2. Oh, there's only one thing. Minus 2. Okay, so we just want to set this equal to 0. 10 minus 2 is 8 minus 0.0002x. If you solve this for x, you get 40,000 items, because x equals number of items. Now, they didn't really ask us what's the maximum items. They asked us what's the maximum profit. So we actually have to take 40,000 and plug it into the revenue, 40,000 minus the cost. They are our original equations. Okay, so plug them into here and here. What you should get is $155,000. Okay, so you will need to check and make sure that is true. All right, last but not, I'm not gonna do that one. Last but not least is the can problem. Okay, what are the dimensions of the lightest open top right circular cylindrical can that can hold a volume of 1,000 centimeters cubed? All right, I drew a picture of the can. I said this is my height and this is my radius, and the volume of the can is pi r squared h. All right, the surface area of that can with an open top is pi r squared, that covers the bottom, and plus 2 pi rh, that covers all the sides. So we're going to use these two equations, and we want to do what? Lightest open top that will hold a volume of 1,000. All right, so the lightest can means we have the smallest surface area, because that's what's going to cost money, is the materials to make the surface. So let's, we know that the volume is 1,000. So what we're going to do is make an equation that is with respect to r. So we're going to, and because we can do that with this equation in volume, we can solve for h. H will be equal to 1,000. I'm taking the top equation, solving it for h. H equals, and we'll divide by pi r squared. Okay, so that equals h. We're going to take this h and put it into the surface area equation. Once we do that, we'll have an equation with only r as our variable. So we have pi r squared plus 2 pi r times h. All right, this is an equation we can work with and take the derivative of and optimize. We'll take the derivative of the surface area and set it equal to 0. Okay, so let's simplify this side just a little bit before we actually take the derivative. We have pi r squared plus, one of these r's is going to cancel out, leave us with 1. Pi's will cancel out. 2 times 1,000 is 2,000 over r. Or we could also write this 2,000 r to the negative 1, since we're going to take the derivative of it. And moving right along with that derivative, remember pi is a constant. 2 pi r plus, well, actually be minus. 2,000 is just a constant. R to the minus 2. Subtract 2, multiply by a negative 1. All right, so now we have to solve that. We'll have to do a little bit of fancy-dancy, not really, fancy-dancy algebra. Let's add 2,000 to both sides. We're solving this for 0. So 2,000, and remember 2,000 r squared looks like this. All right, so I just subtracted the 2,000 r to the negative 2 from both sides, and I rewrote it. Or do I need to do that? Yes, I do. Okay, so now we're going to cross multiply. That's what I would do at least. 2 pi r squared equals 2,000. Now I think we can solve for r. Divide by 2 pi. And then take the square root of that. If you simplify that, you're going to get r. And so r becomes, or was that cubed? Whoops. This is cubed. This is cubed. We have to take the cubed root. All right, so we have the cubed root of 1,000 over pi. I would just leave this number like this. This is your r value. Now you would need to go back to the h value and plug in r to get the actual, you would plug this into r to get the h dimension, because what was asked is what's r and what's h. I think if you simplify this, you get 6.83. Did they give us any dimensions? Nah. Oh yeah, they did, centimeters. Okay, so that is your radius. You plug this r into this equation that we came up with here, and you will find out what h is too. All right, that is the end of our optimizing lesson.